So let's get started with the next topic, that is flow nets. Earlier we were trying to talk about the same flow nets, but in the case of embankments, that's the earthen embankments. So where the flow is going to happen through the cross section of the embankment. So we'll try to talk about how is that the flow net diagram is going to be looking like. I am not going to much details about how to draw the flow net diagram and so on. Just I'll try to tell you the variation, what small variation that we need to understand in the case of your earthen embankment flow through the cross section of the earthen embankment, how the flow net is to be constructed. So that small slide information I'll just try to add to you with respect to already the discussion what we had earlier. Let's say this is the earthen embankment, what I am just trying to talk about. This is the upstream water body. Okay, this additional height what we have here is what we call it as your freeboard. Okay, so freeboard always ensures that you will not have an overflow happening through your embankment cross section. Okay, let's say this is a downstream surface, and because of the total head difference of something, let's say h, your flow is happening from what is called as your upstream to that of your downstream. And due to the flow, what is happening from the upstream to downstream, earlier we were trying to say, okay, the flow would happen from the bottom of the hydraulic structure. It could be a sheet pile, or it could be a concrete dam, or it could be something like that. So where the flow was not happening through the cross section of the flow was not happening through the cross section like this. Rather, the flow was happening only from the bottom of the hydraulic structure, that is through the soil strata, which is there below the hydraulic structure. But here it's an earthen embankment. So once you say it is an earthen embankment, so the structure what we are referring to is an earthen embankment. So once we say it's an earthen embankment, the flow is not just only going to happen from the soil strata which is there below your earthen embankment. Flow can also take place through the cross section of your earthen embankment. So in case if the flow is taking place from through the cross section of the earthen embankment, then how does your flow net diagram look like? So the cases what we had earlier already talked about, if the flow takes place from the soil strata which is there below the hydraulic structure. So in that cases we have already seen how to calculate the flow through that particular soil and so on. Now in case if the flow is taking place through the cross section of the structure, so how do we understand how to construct the flow net diagram? So let me consider this is an impermeable strata. So I have my embankment constructed on some impermeable or impervious layer. Okay, so on top of your impervious layer you have your earthen embankment constructed. So once the earthen embankment is constructed here, and the water storage on the upstream is somewhere here, then what is going to happen? The water tries to flow through the cross section of the embankment like this, and this topmost line, whatever I am trying to indicate, this is nothing but I'll be calling it as your flow line, the topmost flow line here in this particular case. So that flow can happen from what is called as your upstream to downstream, and the bottommost flow line would obviously exist along your impervious strata. Okay, so it's not a confined aquifer, it is an unconfined aquifer. So you have to clearly understand. Obviously, the bottommost flow line is going to be along the impervious strata, but the topmost flow line is something what you should clearly understand. Where is it going to be existing? So this is something what you are additionally required to understand in the case of your flow happening through the earthen embankment cross section when you are constructing your flow net diagram. Okay, so I understood where is my topmost flow line and bottommost flow line. So technically this topmost flow line is otherwise also called as phreatic line, or the surface what is indicated here, this particular surface is nothing but we call it as your phreatic surface. So anywhere on that phreatic line, I repeat, at any point on that particular phreatic line, your pressure head value is nothing but it is equal to 0. What you will have is only your elevation head with respect to any point on that particular flow line what I have indicated here. This is your topmost flow line. So once I understand where is my topmost flow line and bottommost flow line, you will be having other flow lines also in that flow net diagram. And let us look at your equipotential lines. Okay, so at any point along this line, if I am trying to talk about, let's say line AB. Okay, so at any point on this line AB, if I try to calculate my total head value comes out to be same. Okay, so if you want to do, you can try to calculate anywhere here or here or here, wherever you want it. maybe choosing this as your reference datum. So with this reference datum, if I want to calculate what is my total head here, it's nothing but elevation head this much, and the subsequent pressure head is this much. Okay. Here, if I want to calculate, the elevation head is this much, and subsequent pressure head is this much. So that's how I can say simply your total head what you have got is nothing but it is same. So once I understand the total head value along that particular line AB is nothing but it is same, then I will be able to understand now how to construct your flow net diagram by knowing what is your first equipotential line or the equipotential line corresponding to your highest total head value. So once we know that, then we'll go ahead in representing the other equipotential lines. So your line AB is one of your equipotential line. I can say your line AB is an equipotential line. So once we say line AB is an equipotential line, then subsequently we are going to have other equipotential lines which are going to be constructed like this, where I am going to follow once again the same characteristics are the conditions what your flow net diagram has to satisfy. So by satisfying all that criterions, the subsequent flow net diagram is to be constructed. So, oh sir, what is that something new in this particular discussion? There is not much new that we are going to be talking about, but locating your topmost flow line is something very important in this particular flow net diagram, because the other cases are the same procedure what we need to follow. Whether your topmost flow line is going to be like this as mentioned, or maybe something like this, or maybe something like this, or something like this. How is it going to be? Where is your topmost flow line intersecting the downstream sloping surface of the embankment? I repeat, so where is this intersection of your topmost flow line happening with the downstream sloping surface? Whenever the flow line intersects your downstream sloping surface, whenever your flow line cuts your downstream sloping surface, what happens is water particle starts flowing through this surface on the downstream surface. Okay, on the downstream sloping surface, along this water particle starts flowing. If the water particle starts flowing, then you have all possibilities that no soil which is there on the sloping surface towards the downstream, those soil particles will start getting displaced away from that particular location because of the erosion what is going to take place due to the water which is going to flow along that downstream sloping surface. So once there is an erosion, then automatically you over time what we are going to see is that the soil which is in this particular region will certainly have an issue in terms of its stability. The particles will start relatively moving out from this region, and automatically the stability of this particular embankment is going to be an issue there. Okay, so our objective lies in understanding where does this topmost flow line intersects your downstream sloping surface. This end of the embankment, we call it as the toe end. You should find out what is this distance. How much is this length L? Okay, so I'll not be going into the details of derivation part of it. And that value of L upon derivation we'll be getting. So L is that inclined length where your topmost flow line is intersecting the downstream surface of your embankment. So certain information is indicated. So alpha, whenever we are trying to talk about, so alpha is nothing but the slope of the embankment, downstream sloping surface, the angle made by your downstream sloping surface, that angle is nothing but alpha, whereas this angle is nothing but we call it as beta. So you have notations, what does each of those terms represent. So once we understand how the flow net diagram is to be constructed for the earthen embankment, then the rest procedure is the same. Like once we have the flow net diagram, then based on your expressions what we have derived or what we have talked about earlier for estimating your flow through the earthen embankment in the case of flow through the soil. So as similarly here also flow through the earthen embankment, if I want to calculate the same expression whatever we have derived is very much valid. Okay, so into B. So if you are not asked for a particular width of the embankment in its length direction for certain dimension, if it is not specified. So if you are asked per meter length of the embankment direction, so simply this B can be replaced by 1, and automatically you'll be having your Q is nothing but K into H into NF by ND is what is going to be the expression, which you will make use of ultimately to calculate the same thing whatever you wanted. Now here we are going to come across with certain issues like it need not be in the case of earthen embankment, it could be in the case of your previous discussions also. what we have said is whenever the flow is taking place from upstream to downstream, so there is a serious issue of soil erosion or soil particles getting escaped because of the water which is trying to seep through your soil strata. So along with the water which is trying to seep through the soil, there could be some possibilities where you will encounter that soil grains are also getting carried away with the water particle. So in such cases, whenever soil grains are getting carried away with the water particle, then we are coming across with stability issues of that particular hydraulic structure. So to minimize those issues, okay, to address those particular issues, so what we need to understand are, like say, whenever you come across with the issue of your piping failure, okay, even the piping failure can also even happen in this particular earthen embankment also. Okay, let's say for example, I have an earthen embankment like this, and slowly water particles started moving out from upstream to downstream, and as the process took place, then we found that large void path got formed and ultimately resulting in what is called as hollow cross section here. So this complete region is getting emptied, and you will see that strength of this particular embankment is relatively decreasing and resulting in a possible mode of failure. So we have to be very clearly understanding that. So in order to take care of all that particular issues, okay, so what we can think of doing is, let's say for example, if I have got this earthen embankment in which the flow what is taking place through this earthen embankment is expected to cause a kind of failure on this particular downstream region. So what I can try to do is I can think of providing some kind of drainage path. Okay, so drainage path, what does it mean? So you are not constructing some canals there. Rather, you are trying to fill this embankment towards the sloping surface. In the construction of your embankment towards the toe region, okay, this region is nothing but we call it as your toe region, and this is your drainage. Now, what happens is whenever you have a drainage, obviously the water which is trying to flow from upstream to downstream, let's say this is your upstream water level, and initially you had the downstream water level here. Now, due to the drainage what is provided, your topmost flow line earlier you might had here intersecting the downstream sloping surface, but now obviously the flow line has to move towards your drainage. Wherever you have your drainage, water obviously, when you have a rainfall, in which direction the water tries to flow? In whichever direction you have a proper drainage network, so towards that direction the water starts flowing. Okay, in similar way here also, if you have a proper drainage provided, then all your flow lines what you are indicating there, which represents the direction of flow through that cross section of the soil strata, so all the flow lines would go and intersect with your drainage. In the sense, all the flow or the seepage what is happening from upstream to downstream will flow through the cross section of the embankment, and water gets drained through your drainage and it moves properly onto the downstream. So once you provide a proper drainage, now how is this drainage provided? Means by means of what is called as your coarse grain material, which is placed here in the process of construction of the embankment. So you have different ways of providing that particular drainage. Okay, so this we call it as your gravel drain. Okay, sometimes we try to see some drains provided in your embankments. Okay, let's say a drain like this would be provided where all your flow lines would come and intersect to your drainage path, so that all the water particle gets collected into this drainage and water will be easily allowed to go out in the form of providing some outlet point or something like that. So through those outlet points or through any pipe connectivity, water tries to flow easily onto the downstream side without causing any kind of failure to your downstream sloping surface. So if you don't see failure getting initiated onto the downstream sloping surface, obviously the stability of the structure can be ensured, and you need not worry about the strength aspect of this particular embankment. So your embankment, for whatever purpose you have designed, so that purpose is going to be met. Okay, so this kind of drainage, I can call it as your blanket drainage or blanket drain. Sometimes we also have a drain of L-shaped cross section. Okay, so which I can call it as your vertical blanket drain. So, like, depending on your requirement, we have got different types of drains, different mechanism of providing the drains are available. So now what is the material that you are going to be providing here? Means, are we trying to construct any kind of separate structure inside your earthen embankment. It's not that very particularly we are constructing some structure. Rather, in that particular region, instead of providing the same fine grained soil in the construction of the embankment, there in that relevant region, we are going to place what is called as a coarse grained material, or maybe some geosynthetic materials, so that your so-called of water which is trying to flow through your earthen embankment can easily pass through that particular path what you have provided for a purpose of a proper drainage. Okay. So in order to ensure the safety of the structure, so we try to go on to provide such kind of drains. So let's go ahead in understanding. So how these drains are provided, what are the factors that we need to take into consideration in the design of proper drainage, or in the process of providing the drains. So what are the different steps that we need to be taking into consideration? So all those steps I'll be certainly talking about now. So filter design. A filter is nothing but your drain, whatever I am trying to provide. So that drain is nothing but I am calling it as a filter. Why I am calling it as filter means purposefully we will call it as filter, not just by simply calling it as a drain. Okay. So what does the word filter mean? So filter is nothing but it's a medium which is trying to filter out certain particles, not allowing those particles to get carried away with the water. So in the case of your piping issue or the erosion, whatever we are trying to talk about, what is that we have particularly said is, when the water particle is trying to move from upstream to downstream, there is a possibility of soil grains getting carried away with the water particle. So to prevent the escaping of your soil grains from that soil medium, so for the prevention of to prevent the movement of your soil grains from its position, so we are going to provide what is called as a proper drain, or we also call it as a filter. So as mentioned previously, piping and erosion are a possibility if somewhere in the porous medium the gradient exceeds your critical gradient. So already we have talked in the last class, whenever your exit gradient, okay, towards the downstream sloping surface, so whenever your exit gradient, what you are coming across for that particular soil is greater than that of your critical hydraulic gradient, then automatically we say your piping failure takes place. So in order to prevent that such kind of piping failure where you are seeing fine grained particles getting carried away, so in such cases, if I can provide this proper drainage or proper filter medium, so that your fine grained particles will not be allowed to get escaped with the water particle, and your fine grained particles remain there itself, to ensure that there is no such kind of failure called as your piping or erosion happening towards your downstream side. Piping can occur at any place in the system, but usually it occurs where the flow is concentrated. So piping obviously happens through the soil strata wherever possible, but most possibly you will be seeing in the region where your piping gets initiated. Where are we going to have this piping getting initiated means in the region where flow is more concentrated in the sense your flow path is relatively smaller, but the quantity of discharge has to be same through each flow path when we are trying to talk about. So through that smaller flow path, with higher velocity the particle starts moving out, then only you can say the rate of flow is going to be constant with respect to each of the flow path. So in such case where your rate of flow, what is happening, or the velocity with which the flow is taking place through the soil is more, then in such case we say the flow is more concentrated in that region. So in that region where flow is said to be more concentrated, you have possibilities of having piping getting initiated through that soil strata or in that particular flow path. When seepage water flows from a soil with relatively fine grains into a coarser material, there is a danger that the fine grain soil particles may wash away into the coarse material. Like say, if I am simply providing what is called as a drainage, so without understanding what is the purpose of providing the drain by means of what is called as the coarser material which is placed there. So the coarser material which I am trying to talk about in the previous slide when I said, okay, this coarser material which I am trying to provide here, this is going to be helping me in what is called as a proper drainage. Okay, so that's nothing but improving the permeability of the soil condition so that water can easily flow into this particular path of what I have provided. Okay, that is one important thing. And the second important thing is this drain should not be only allowing the water to get passed away, and it should also act like a filter. What does this filter mean? It should not allow your fine grained particles to escape through this particular soil mass. So it should also act like a filtration medium. So when you are trying to provide a drainage in a way by means of using the coarse grain particle, so all the fine grain particles whichever are there in this embankment, during the process of flow, if I have one fine grain particle, another particle, these particles should not go and get accumulated into the large white space of your coarse grain material which is placed there. So that's how you should not provide proper drainage there, because larger the void size, easily water will escape through the void, whatever is available in your coarse grain material, what is placed. But there is also an issue that if larger is the void space, it is obvious that your fine grain particles can easily escape. So there is a danger that the fine soil particles may wash away into your coarse grain particle, and then subsequently get sometimes those particles gets deposited only within your void spaces of that coarse material, or sometimes those fine grain particles also completely moves out of your soil towards the downstream. Over a period of time, what we are going to see is that this process may clog the void spaces in the coarser material. So if fine grain particles are getting escaped from that soil medium, and those fine grain particles are getting deposited into the void space of the coarse grain material, which is provided in the form of a drainage, then over time, after some period of time, there is all possibilities that clogging takes place in those void space of the coarser material. So hence the grain size distribution of the coarser material should be very properly manipulated to avoid this particular situation. So you have to choose your coarse grain particles of sizes according to the proper design. Then only you can ensure that such kind of clogging do not happen in that particular drain. There are several methods to control seepage and to prevent erosion and piping. One of such is to use what is called as a protective filter. So such kind of protective filter is nothing but we are calling it as your drain. A properly designed coarse material is nothing but we call it as your filter. A filter consists of one or more layers of free draining granular materials placed in less permeable or less pervious foundation or base materials to prevent the movement of your soil particles, okay, that are susceptible to piping, while at the same time it should also be ensuring to allow the seepage water to escape with relatively less head loss, or relatively with little head loss. You should allow the water to be flowing even through your coarse grain particle also, because we are providing it to facilitate what is called as a proper drainage. Okay, so drainage of what? Drainage of your water which is trying to seep through your soil strata there. Yeah, so this is the case what I was just trying to refer to. This was an earthen impermeable strata, and this is your earthen embankment. This is the direction how your seepage is happening into your drain, which is provided there. So I can even call this drain or filter as nothing but toe drain, because towards the end of your towards the toe position of the embankment it is provided. So I can call it as your toe drain or toe filter. So basically these filters are used for the purpose of facilitating the drainage. Okay, so whatever water that is trying to seep through the embankment, so you cannot stop that seepage. Okay, only thing is that though the seepage is taking place, there should not be any issue to the structure. That particular thing we have to properly ensure. So for that, I have to see that a proper drainage path is provided. You have to facilitate the process of seepage without causing any kind of issues to your structure. And next is preventing fines from being washed away. I have said already, like the filters, whatever you are trying to provide, the drains, what you are trying to provide, the purpose of those filters or drains is to ensure to take care of two things. Okay, one is to allow the water seepage properly, okay, without having any issue. And second is there should not be any escaping of fine grained particles. So that's how your filters are to be properly designed. So in which all places we most commonly think of providing these particular filters means, so these filters are provided most commonly in the case of earthen embankments or earthen dams and retaining walls. Okay, we'll just try to see those slides and we'll get a clarity of what is that I am talking about in the case of your retaining walls. Now, what are the materials by which these filter mediums are prepared? Are these filters are whatever I am trying to talk about? They are made of what? They are made of mostly the granular soil materials, that is your gravel particles relatively of larger particle sizes. So those materials are going to be placed, and geotextiles can also be used, because geotextiles, what is the function of the geotextile? Geotextile allows the water to seep through, and it also acts like a filtration medium, because it will not allow the fine grained particles to be carried away with the water particles. So that's how you can think of not just only your granular soils, you can also even think of geotextiles and various other geosynthetic materials like geopipe. Okay, so various other such kind of things can also be thought of, so that you can minimize your failure issues what you are expected to have in your structure. Yeah. So when you are coming across with the case of your retaining walls, okay, so in the case of retaining walls, how does this filters going to help you? Like say this is all your soil in the case of retaining walls. So this most in detail, like what is this all about, we'll try to talk in your foundation engineering course, the first unit of your foundation engineering course. Look at here, the soil, whatever you have here in the complete region is not same. Okay, towards your retaining structure, this vertical member, whatever you have here is nothing but we are calling it as your retaining structure. What is this structure doing? Why do we call it as retaining wall or retaining structure? Because this structure is trying to retain material. Which material? Soil material on one side at higher elevation. On the other side, you need not have the soil, or you might have the soil to some relatively lower elevation. So the purpose of the retaining structure is to retain the material. Which material? It could be soil, it could be even any other materials if you want to retain at different elevations. So you can make use of your what is called as a retaining structure. Now, due to the excess pore water pressures which built up in this particular region of the soil, what would happen is, if pore water pressures are more, then the effective stress what we are going to calculate, which we write it as your total stress minus pore water pressure. So what would relatively happen is, if this particular soil, what I am trying to talk about, let's say for example, it is a clay soil deposit. If I talk this to be a clay soil deposit, so clay, the relative coefficient of permeability of the clay is very small, and over time, what we are going to see is that your water particle, whatever is there in the small void spaces of the clay soil deposit, requires more time to get dissipated out of that soil sample. So in the process, if there is any external loading acting on this particular soil strata, maybe because of any superstructure, or maybe because of any external loading acting on that particular ground surface here, so you will see certain situations where the pore water pressures building up in that particular clay soil deposit, this pore water pressures will continuously increase. Why is it increasing? Because the water particle is not finding a free space to easily come out of that particular soil. If the water particle is not finding a free space to easily come out of the soil, then the pore water pressures which are building up in the soil will continuously increase. And if the pore water pressures are continuously increasing, then automatically the effective stress, what we are going to be talking about, starts coming down. So if the effective stress, what is getting developed, is coming down, then automatically the load carrying capacity of this retaining structure, which we are trying to talk about, also comes down. Okay, so in order to see that excess pore water pressures do not build up, so if I want to ensure that excess pore water pressures are not getting built up, then what I have to do is I have to plan to provide what is called as a proper filtration medium. This coarser material, whatever I was just trying to refer to, what is it going to do? Once the water is trying to come out of this clay soil, so those water particles can easily get escaped into the large void spaces which are available in the form of your coarse grain material, and all those water particles which got accumulated into this coarse grain particles will get drained into a pipe. So you could see a kind of a pipe which is provided here. So all that water gets collected into that pipe, and through the pipe, water can easily get drained out of your soil sample. So that coarser material, I am calling it as your granular soil. So you are going to provide adjacent to the retaining structure a granular soil, so that water dissipation can easily happen through that granular soil, and then water gets easily drained out of your drain pipe which is provided there. In similar way, so you also have what is called as look at here in the next image. Okay, in this image, so you have this is your soil. Adjacent to the soil and to the retaining structure in this region, we are trying to provide something what is called as your geosynthetic material. Okay, so this geosynthetic material would try to ensure to allow the water coming out from this soil. So your geosynthetic material allows the water to seep through that material, geosynthetic material, and in the form of what are called as drains, which are provided somewhere at the bottom or somewhere in between the cross section of your retaining structure. Water gets drained out of that geosynthetic material. Likewise, in the similar way here, so this is your compacted soil, and this is your, let's say, coarse grained material. Okay, so once we say it's a coarse grained soil or granular soil, and here is some geosynthetic material. So what is going to happen is, geosynthetic material, what is provided there, acts like a suppression medium, so that all the fine grained particles will not get entered into your coarse grained medium and clog the void spaces which are available there. And it also ensures that a proper form of drainage takes place through your soil, and it can also increase the stability of this particular soil which is existing in this particular region. It increases the bearing capacity of the soil in this particular region. So you have got different advantages by providing a proper drain or a filtration medium, so that you can minimize the issues of issues in the case of your retaining structure. So the two major criterion that we have to take into consideration when we are trying to design any filter is, one is retention criteria. What does this retention criteria means? When the fine grained particles are trying to move out of the soil, so your filter what you have provided should ensure that those fine grained particles will not get washed out of that particular soil. So filters grains must not be too coarse. So in the sense, the soil grains which are used, okay, so the soil grains which are used in the process of preparation of your filter should not have the size of the particles which are relatively very high. If they are very high, what happens is the size of void formed in between those particles is also a little bit bigger. In the process, your fine grained particles cannot get trapped there. They also easily get washed out of that particular soil. So your filter should act like a retention medium, and it should also act like a permeability criteria. What does this permeability criteria means? The purpose of providing the filter there is also to allow the drainage. Okay, so allow the seepage water to easily pass from upstream to your downstream. So if I want to allow the seepage to happen without having or without causing any failure to the embankment, so I am trying to facilitate a proper drainage and thus avoiding additional build-up of your pore water pressures. So if you are allowing the water to easily get drained, so excess pore water pressures will not build up. And if excess pore water pressures are not building up, then effective stress developed in the soil will not come down. If effective stress is not coming down, then the strength of that particular soil is going to be relatively high. Next. So in selecting, now how is that filter materials are to be chosen? There are certain criteria which are to be followed. Okay. So like US Navy has given certain criteria, Sagi and Peck has specified some criteria. Likewise, Indian standard codes, you will have some specific criteria. So whenever you are trying to talk about the design of filter, so certain criteria that are to be satisfied in the design of the filter is, filter what you are trying to provide should facilitate a proper drainage through that filtration medium, and second is it should not allow the fine grained particles to get escaped through the filtration medium. So that's how by satisfying these two conditions, these two criterion, you have to go on to design your filter material. Okay, so according to Sagi and Peck, you can design your filter by satisfying these criterions. Like say, you understand what is D15, D85 and so on, all the numbers you already have come across with. What does F here refers to means? F refers to filter and S refers to soil. Okay, so the soil in which your seepage is taking place. Okay, so the D15 value of the filter, the ratio of D15 value of the filter to that of your D85 value of that particular soil in which the flow is taking place, this ratio should be less than or equal to 4 to 5 to satisfy this particular first condition what is listed above. Okay, and next is the D15 value of the filter, the ratio of D15 value of the filter to that of your D15 value of your soil should be greater than or equal to 4 to 5. When I am calculating this ratio, it should be in between 4 to 5. Then I can say this second condition is also going to be taken care by that particular filtration medium what I am going to be using in the construction of the filter there. So likewise, you have got like how to calculate, how to pick out your D15 for the filter, D15 for soil, D85 for soil, and so on. That already, you know, once we have the grain size distribution curve for that filter material. So from that grain size distribution curve for the filter material, I can pick out your D15 value of the filter material. And likewise, if I know the grain size distribution curve for the soil in which the flow is trying to happen, okay, then for that particular soil, I can determine D15 and D85 value. So once D15, D85 for soil is known, D15 for filter is known, then I can calculate those respective ratios what are listed above in the previous slide, and based on that, satisfying the criterions, then I can judge that okay, that particular filter material is proper to be provided in the design of your filter. Likewise, according to US Navy, you have certain criterions which are to be satisfied in order to provide a particular, in order to say, okay, this so and so filter material is proper in the design of your filter. So you have various criterions which are to be satisfied. So it's very much clearly understood, all that whatever are mentioned. So all those subcategories of conditions are to be satisfied, ultimately to say that your so-called filter, what you are trying to design, will ensure the safety and the stability aspect of that particular structure there. Okay, so with this, I'll conclude your unit. That is nothing but flow through soils, stresses in the soil, and seepage through your soils.